Hello, everyone. Welcome to the Temporal Graph reading group this week. Um, we are very glad to host Bardh Prenkaj. Uh,
Prenkaj. Yeah.
yeah, Bardh Prenkaj, who will be presenting their recent work, Unifying Evolution, Explanation, and Discernment, a generative
Mhm.
approach for dynamic graph counterfactuals.
Mhm.
I will start with the speaker introduction.
Mhm.
Um, so Dr. Bard is a postdoc in AI at the Technical University of Munich, trying to understand what makes us or not human, and what actually is machine intelligence with Gerd Jag.
Jerzy Gasnetsi. Yeah,
Okay,
I'm in his chair.
go. Um, from October 2022 to October 2024, he was a postdoc at the Sapienza University of Rome in anomaly detection and explainability, and he received his PhD in 2022 and his master's in 2018. Um, and he also had experience working in Rome and as a senior researcher at the CS department. Um, yeah, so I will hand the mic to you.
Okay. Thank you again, Andy, for having me, and Julia for getting back and forth with the emails to me. Okay, so as far as it's concerning about questions or answers, you can either just stop me throughout my presentation, or you can have them at the end, however you feel more comfortable. Today I'm going to present my paper, which was an oral, let's say an oral presentation, got an oral presentation at KDD 2024. So I was in Barcelona not that long ago. I'm aware that the title is a bit long, so we have to thank my colleague for this long title. But for short, I'm going to refer to this paper as Gracie, which is the method that we're going to basically introduce throughout this talk. Okay, so let me just showcase what the poster looked like. Probably not the most, let's say, standard poster that you've seen in conferences, at least in my opinion. I've attended a lot of conferences and I've seen the same template over and over again. And here I just wanted to be more creative and just showcase my research in a let's say newspaper fashion. The poster got very much traction. People just stopped because it was cool. People took pictures, not because they were interested in in my approach, but because the poster seemed very interesting. Okay, so what are we going to do in today's talk? What we're going to treat? I'm just going to bring to give a brief introduction on graphs. I am fully aware that because this reading group is about graphs, you all know what graphs are, but it doesn't hurt just to brush up our memory sometimes. Then I'm going to delve into what are counterfactuals and what is counterfactual explainability. And then I'm going to give some motivation about this work based on a paper from Pawelczyk et al. From the University of Tübingen here in Germany, and the paper is titled The Right to be Forgotten. It just treats something where data points might get deleted in time, and what do you need to do to basically improve your explainability when data is erased. Then I'm going to give a pictorial problem statement because I think that this paper is very heavy in formalization. So something that is very pictorial might help the audience grasp the meaning of this paper. Then, of course, just some math. I'm going to go into a bit of details, although it's not going to be very math intensive. Although, if you wish to ask some questions about this kind of formulation and formalization, I'm happy to address them. Then I'm going to move into something that is called generative classification. There's this distinct two types of classification. It can be either discriminative or generative. Here we treat generative classification and how we're going to use reconstruction-based, let's say, methods and a generative classification, such that to build a bridge between counterfactual explainability and reconstruction-based methods. Um, Next, I'll present Gracie, which is the method of this paper, how the training is done, how inference is done, and how we find latent counterfactual explanations, and how then we update our method. Some experiments that I'll showcase, so such as synthetic versus real data, and versus real world data set, sorry. There's this called pulling factor, which will go into more details when I will explain the method and what's the trade-off between being correct and being very close by. And then some qualitative inspections, because I think that this is one of the first works that shows how to qualitatively inspect the counterfactuals that are generated in graphs, but not by showcasing a graph with nodes and edges, but using something more interesting. And lastly, yeah, I'll go into conclusions and takeaway messages from this paper. Okay, yeah, let's just begin with the concept of a simple graph. We all know that graphs have nodes and edges. Nodes might have attributes. Edges might have also weights, or might also have attributes which could be vectors, but just for simplicity, let's assume that they're just weights from 0 to 1. In some of the formulation of graphs, you've seen that it consists of two sets, V and E, where V is the vertex set and E is the set of edges. Just for let's say being more comfortable with what graph neural networks take into input, I'm just assuming that you have a node feature matrix and the adjacency matrix. So if we have n different nodes, then the node feature matrix will be in the domain of real numbers. So it's going to be n times d, where d is the dimension of the features, and the adjacency matrix is just a square matrix of n by n. Okay, so this is just a simple graph. Now, what we use in this paper is not just simple graphs. We're using time-based graphs, or different snapshots of the same graph evolving in time. Let's assume that we have a time dimension that goes from t0 to t to tm of the same graph. And we can assume that the first graph, so the graph at snapshot t0, is a base graph structure. And then we can trace its mutation in time. So for example, if we take g of tj, that's the graph mutation in time, or a snapshot tj. Some of the assumptions that we make in this paper is that there are two different possible modifications in time of the graph. You can have node additions or removals, and you can have edge additions and removals. Moreover, you can also have feature perturbations of the nodes and feature perturbations of the edges. So these are four different kind of modifications that you can have in a specific graph. Now that we've treated what graphs are, I'm just going to touch base on what are counterfactuals. And it's very simple. Let's assume that we have a black box model, which is this phi here. So this is in this case, might be a linear regressor, which basically separates the data points into two different classes, so class blue and class red. Now, for any given data point G, so if we suppose that these data points are graphs, for any given graph G from class blue, I need to find another data point, so another graph G prime, which lies at the other side of this decision boundary phi. So in this scenario, we can see that G is associated to G prime, and the necessary condition for a graph G prime to be a counterfactual of G is to have different outcomes with respect to this black box model phi. Okay. Throughout the talk, I'm going to use the term oracle to indicate this black box model phi, because we assume that this oracle is omnipotent and can know everything. Okay. And based on this oracle, we want to explain, we want to engender different counterfactuals for each of the data points. Now, I'm moving to this to the motivation of our paper. Pawelczuk and his colleagues have done this this paper, which was presented at ICLR So I guess like 2 years ago, a year ago, something like that. And it treated this problem where, according to the European GDPR guidelines or regulation in this case, people can just choose to have their data deleted from a system. And if somebody has trained an Oracle fee on that data, whenever this data, which personal data, which was opted to be deleted or to be forgotten, then something might happen with fee. So the decision boundary might change. And if somebody was using some counterfactual explanations on that Oracle fee, then because the decision boundary changes, then also the counterfactual explanations for each of the data points should change. So the gist of this paper, if you read this paper, it has like 150 equations, man, and you have to read it like 100 times to get it. But the gist of this paper is, okay, counterfactuals can become very invalidated when data is deleted. And they actually identify those data points, and when deleted at a time step or snapshot t plus delta, it will invalidate most of the counterfactuals at the time t. So if you have this simplified classification boundary from class 0 and class 1, and you have a data point x, then if the original boundary was this f of w1, then okay, x1 tilde would have been a nice recourse, a valid counterfactual. So with recourse, they also refer to counterfactuality. So this would have been a valid counterfactual example for x. But if the decision boundary is updated, as I said here, then this is completely an invalidated counterfactual example. So based on this, we draw a parallelism on this time on time graphs where the same graph in different snapshots might change either classes, or it just might be different such that it updates the model's decision bound. So let me just show you a pictorial problem statement of our paper and why we think that updating counterfactual explanations in time when data has distribution shifts is very important, as also suggested by the last paper that I just showed you. So let's suppose that we're at snapshot t. We still have our good old Oracle P, which is a linear regressor here, separates the data points into two classes. What we for a graph G1 at time snapshot T, we want to find a counterfactual, right? But here, notice that in the previous slide, where I showed you the definition of what a counterfactual is with respect to the Oracle fee, I just chose any kind of instance that is on the other side of the decision boundary. So in this example, in this figure here, we can see that G3 at the same snapshot is a valid counterfactual example for G1, right? Because it stands on the other side of the decision boundary. What we want also, and this is something based on a paper of Sandra Wachter, which was published like I think 5 to 6 years ago, which delved into this kind of counterfactuality aspects. One of the desiderata in her paper was that the counterfactual example, so the example that stands on the other side of the decision boundary, needs to be as similar as possible to your input that you're trying to explain. So similarity can be intended as structural similarity, for example, in graphs, same nodes, same patterns of edges, or it can be measured as distance. Maybe you can encode these two graphs using a graph convolutional network into an embedding space, and then compare their vectorial representations and see whether their, let's say, cosine similarity is high enough. Okay, and notice that deliberately here, again, these definitions of counterfactual explainability are based on similarities or are based on distances, right? So you need to be very close by the Oracle decision bound. However, here deliberately, I've chosen to depict probability densities here. and we approach this, let's say, this counterfactual problem according to a probabilistic point of view. What we want is not to use distance or similarity. We want to use the most probable graph the most probable graph on the other side of the decision bound. So given G1, we might have a counterfactual candidate G3, but this G3 is not the most probable with respect to G1. The most probable with respect to G1 is G2, which happens in this case to be in the most dense region of the probability density, right? So this is a simple scenario, again, at snapshot T. What might happen at snapshot T plus 1, so we go from here to here, look that the density regions now, the probability regions now, are actually intertwined, and they have shifted somehow. Not only the regions have shifted, but see that G1 in the previous snapshot T now has completely changed its true class. Maybe it has its nodes removed. Maybe it has its edges removed. Node features have been perturbed or something, but the true class of G1 at the previous snapshot now is completely different, right? And if we take now the new graph here, we definitely cannot have, sorry, this is a slip, this should be G2. We cannot have this data point as its counterfactual because it's actually not a valid counterfactual anymore because it stays on the same side of the class. So it cannot have the same class. So the first necessary condition is violated here. And you can see that with the dashed line, the new, let's say the old decision boundary cannot actually correctly represent the new data distribution shift. So it gets invalidated. So this was the gist, pictorial gist of what Pawelczuk and his colleagues were trying to say in their ICLR paper. Now, what might happen here is you can say, okay, let's just retrain the Oracle model, and let's see whether we can fit, maybe with a neural network, we can fit a new decision boundary, provided that we have some misclassification, but that doesn't matter. And maybe with this new decision boundary, we can figure out whether we can correctly reassess the counterfactuals and update them. Now, in this paper, we don't want to train the underlying Oracle, because in real cases, real scenarios, this might not be feasible because maybe it's a very huge model and it takes too much time to retrain. Yeah, maybe we don't have access to the data set, stuff like that. No, so we just want to operate at instance level without touching the Oracle. Okay, so what might happen is that because now imagine that the new decision boundary has been magically updated somehow. What we can do immediately is we can find another data point on the other side of the new decision boundary and actually update the counterfactual of G1 into this GK. Okay, so imagine this procedure going on for delta snapshots. Okay, until the time has ended, the monitoring time has ended. Okay, so this was, let's say, a pictorial motivation for our paper. I will move on to more formalisms of this let's say, pictorial motivation. And again, just to go again into what counterfactuality is. Here we approach counterfactual explainability under a probabilistic point of view. And if we have an input graph GI at time step T, in that particular time step, we want to maximize the probability such that any other kind of graph GJ on the same snapshot belongs to any other class that isn't the class or the prediction of GI with respect to the Oracle C. And we want to maximize this probability. So again, differently from previous work, here we shift our focus to a generative classification perspective. And what is cool about shifting towards this kind of point of view is that the probability of we can ensure that the probability of any other counterfactual Gj with respect to Gi means that Gj is in distribution. So it's a counterfactual which is in distribution of the original input. Now that means that we ditched the similarity and the distance function, and we are now treating just distributions, right? So this is the mathematical formulation of our paper. Now, why do we choose to have a generative classification perspective? We don't do this just to be fancy. We do this because it's more reasonable to perform a classification by modeling the full joint distribution of features X and class labels Y, instead of performing discriminative classification where you learn the probability of Y given X. Here we want to learn the joint probability, or in more interesting, we want to learn the probability of Y given of X given Y. So this is a formalization of how you can do generative classification instead of doing discriminative classification. One of the reasons that we chose, and this is based also on previous work where you do generative classification, is that you have superior generalization capability over discriminative classifiers. You can have you can accurately calibrate different posteriors, and in this case, because we want to be also fair, so we want to learn something that is fair and generates fair counterfactual explanations with generative classification perspective. Adopting this perspective, you can have an increased adversarial robustness. All of these three different statements have been supported by previous work, and you can just go and look at these works that support these claims. Now, just as a preliminary, I still haven't delved into what Gracie is, but just as a preliminary, we are going to use variational graph autoencoders. So just to give you a gist of what an autoencoder is, it basically is like a neural network which has a bow tie shape. It takes an input, let's assume that it takes an input, a graph, and in output, it tries to reconstruct the graph as faithfully as possible by minimizing, for example, a loss, which in general might be a mean square error loss. So that's an autoencoder just briefly. Here we consider variational autoencoders, where the graphs G from this variational graph autoencoder are generated from a factored latent representation Z and the true class label by following basically this formula here. So if you have a label Y, then you can generate G by first encoding this, by using this latent representation and generating new graphs. The cool thing about variational graph autoencoders, but in general also variational autoencoders, is that after they're trained, you can sample their latent space. You can sample from their latent space and generate new data instances. Okay. Let's first describe the decoder of this variational graph autoencoder and what it is. So if we want to represent the probability of a graph G given Y, we can use a single variational graph autoencoder for each class. And I'm coming to my motivation of using one autoencoder for each class. Just bear with me, which is dependent on the class where the node has a latent vector. And then we can define basically, so this is a decoder based on parameters theta of Y. Of G, we said that G can be represented as an adjacency matrix and node feature matrix, and this latent representation. And then basically you can just use classical probability properties to basically just learn this, the reverse process of the encoder, so the decoding process. And an encoder is basically, we denote it as Q. It has a different parameter phi instead of theta, and also an encoder has parameters based on the class. And what it wants to do, it basically takes a class and the input graph, and it needs to learn this latent representation Z. Usually this latent representation Z is learned per node. So we simplify this latent representation as being the product over the different nodes of the graph. So you need to learn basically a latent representation for each of the nodes. And usually you have this encoder for each node is based on a Gaussian distribution, which has a mean for each of the nodes and basically a covariance matrix with this hyperparameter, which we fine tune. Usually the means of each node of this Gaussian distributions are estimated through a graph convolutional network based on the input graph, which has the same parameters as the encoder. So basically, it's just a component in the encoder to learn these means. Okay, so now that we have everything in place for variational graph autoencoders, we have come up with an interesting theory. So basically, based on what was already established for variational autoencoders, we can basically train also variational graph autoencoders for each of the two classes by optimizing both the parameters theta and phi. And that can be done by maximizing the elbow of the two, which is basically the combination of the I'm just going to go through this in plain English and not just go into maths. So basically, this is the first term tells you whether you have actually reconstructed correctly your graph, your input graph, given y and given the latent representation z. And then you also need to basically, let's say, minimize the KL divergence between the latent representation of the priors. Okay, and you do this for both for all classes in your data set. And again, I'm coming to the reason why we use multiple classes. In this work, we concentrate only on binary classification, but the formalization is fully extendable to multi-class classification. Why binary classification? Because usually the data sets the data sets that we use are for binary classification, and it's actually very easy to imagine counterfactual explainability in binary classification scenarios. Whereas for multi-class classification scenarios, counterfactual explainability, at least in graphs, has still to see a complete formulation and a nice, let's say, data set that tackles multi-class classification. Okay, now why do we use autoencoders and generative classifications? I told you that autoencoders have this reconstruction error, which they try to minimize, which is basically what's happening here. And generative classification is that if we have, let's say, a variational graph autoencoder, which is an expert at representing a specific class of graphs, then we can use these experts, so these variational graph autoencoders, to perform generative classification. How? The intuition is that if a graph at inference time, if a graph belongs to the representational class where the variation graph autoencoder has been trained on, then the reconstruction error will be very small. This is what is expected. If the graph in input at difference time doesn't belong to the class that the variational graph autoencoder has learned to represent, then the reconstruction error will be large. So one can know if one can do binary classification just by having a fully unsupervised approach with variational graph autoencoders, because one can just see whether the reconstruction error, which of the reconstruction errors is high. And if the reconstruction error is very high, then you can say, oh, okay, this doesn't belong to class 0 where I'm trained at. This belongs to class 1, and vice versa. So you can do that. And you can do that. We actually formalize this and use it to perform generative classifications. Is you can use reconstruction losses to perform implicitly classification. So if the density model that we described before is sufficiently expressive, then it's basically, we can use this formula here as to perform generative classification for the input graph. So this formula here says that we can choose, so the gist of this formula is we can choose the class which has the lowest reconstruction error. So if we have two different autoencoders, one trained on class 0 and one trained on class 1, we feed the input to both of the autoencoders and see which of the reconstruction errors is minimal. If it's the reconstruction error based on the autoencoder trained on class 0, then the outcome will be 0. If it's the other way around, then the outcome will be 1. So this is the intuition behind having autoencoders in general, or reconstruction-based methods in general, to basically perform generative classification. And here, G is the decoder and F is the encoder, just to showcase you what the notation is. But yeah. Now we move into our method, which is called Gracie. Again, I prefer to name this paper Gracie, but the title is what it is. And here we come to the reasoning why we use several variational graph autoencoders, or as we call them, class representation experts. So imagine that we have a data set of graphs here, and we have this oracle phi, which is a black box. And here we're talking for we're in the first snapshot. So we're at time t0, where the decision boundary of the oracle is perfect, so it can correctly separate the two classes. And what it does then, we can have for each of the graphs on our dataset, we can train two different variational graph autoencoders, which are these class representation experts. So this variational autoencoder here will be the expert for class 0, and this variational graph autoencoder will be the expert for class 1. And all of the data based on the outcome from the oracle get basically redirected to the graph autoencoders. And each of these graph autoencoders just trained to minimize the reconstruction loss of the graphs and to minimize the KL divergency between prior and the learned latent distribution. The same thing. So here
just a quick question.
Yeah.
Sorry. Just a quick clarification question. So the oracle is given, so you know the labels?
The oracle is given, yes.
Okay, thanks.
You're welcome. So you can see immediately here from this graph pictorial representation that the variational graph autoencoders are forced to learn a space, so a latent space, which resembles a circle. And the idea here is that, so the variational graph autoencoders, and I'm going to go into how they train, but the gist of the training of the variational graph autoencoders is to not only learn how to correctly reconstruct graphs of the same class. So for example, if we take the variational graph autoencoder of class 0, it is not only trained to correctly reconstruct graphs of class 0, it also wants to pull those latent representations towards the center of its space. So here the space is not necessarily a circle or a space, but the idea just of representing it as a circle makes it more popping, because what we want is the knowledge of our expert to be good at reconstructing, but also at the same time mapping them towards the center of the space. And I will show you in the next few slides why this is important. So I just mentioned you how they trained, but for each of the autoencoders, we minimize this elbow here on both the parameters of this is the decoder and the encoder. So what we want is we want to minimize the reconstruction loss and the distance loss. So the reconstruction loss is this guy here, okay? And the distance loss is basically this one. And notice that G is a decoder and F is the encoder. What we want to do is I think I have something on the chat. Let me just, okay. Sorry, I got distracted. So the minimization of the distance is on the encoder side. And what does the encoder do? It just basically takes the graph and maps it to a latent space. And what we want to do is we just want to minimize the L2 norm of that latent representation. By minimizing the L2 norm is just another way of a fancy math way of saying, hey, pull this latent representation towards zero, so towards the center. And the more you pull, the better you are. Now, obviously, you might say, hey, but you're doing a stupid thing here because you're learning a shortcut, because if I just learn the numbers, so if I just multiply all of my latent representation by zero, then I'm done. I'm basically done. But this is not how it works, because otherwise you're not learning how to correctly reconstruct the graphs. Okay, so these two losses need to be in trade-off. You either want to learn them, you want to learn the input graphs correctly, or you want to just represent points at the center of your latent space. I don't know if I have a chat. Okay, nice. Okay, now that we assume that we have trained these two class experts, two class representation experts, so these two variational graph autoencoders. Now, what we do at inference time. Now, assume that at inference time, we have a graph that we've never seen before. And this graph that we've never seen before is this G star, right? Sorry for the quality of this image, but I think that it's still visible. Anyway, this graph G star comes in input. What we can do is we can use the formula that I told you for graph, for generative classification to determine this y hat. And in simple English words is take this graph, throw it into both of the autoencoders, and see which one reconstructs it better. And let's say that autoencoder 0, graph autoencoder 0 reconstructs it better. So the outcome here will be 0. Now, because the outcome is 0, now this is a question for the audience. If this graph has its class predicted y hat equal to 0, where do you think we should search for counterfactuals? In which of the autoencoders? Any idea?
The one with the 1?
Exactly. So the opposite one. This is why, exactly. This is why we use this, let's say, generative classification property of variational autoencoders, because you can actually determine where to find counterfactuals. And notice that it's very neat that we have separate class representation experts, no? Because we can find counterfactuals on the opposite autoencoder. So let's assume that this graph here, as you can see, this graph here has cycles, right? And let's suppose that the task to find a counterfactual is to find a graph without cycles. And a graph without cycles is just a tree, okay? Now, let's suppose that we map this this graph on the latent space of the opposite autoencoder. So we map it to this data point Z. And then what we've known, because the variational graph autoencoders are trained to learn to reconstruct goodly their graphs, but also map them towards the center of the space, the valid counterfactuals that we want to find, so the most probable counterfactuals that we're going to find are going to be centered around the space. So if we map this graph to this data point Z, then we can have a pulling factor lambda to pull this latent representation to the so-called Z star and find the data points on the current snapshot that could be potential counterfactual candidates. And notice that these highlighted triangles, so the green triangles, might represent valid counterfactuals because they're mapped towards the center, whereas something that is, it might happen that something is mapped, although we've minimized the distance, it might still be that something is mapped a bit far away from the center. So these red squares are not going to be considered as valid counterfactual because we're pulling towards the center. So at inference, we find counterfactuals like this. We map them to the latent space, we pull them, and then we can sample here. So we can just say, hey, look, you either just find data points that have been mapped here, or you can actually sample from Z star and generate actually new counterfactual explanations. In this paper, we limit ourselves into just having a simple distance function and just say, yeah, let's just take the top 10 counterfactuals, data points that are close by or nearby Z star. But in future work, we will definitely explore the fact that Z star is now can be sampled, and you can sample from this and actually generate more different counterfactuals. And that we argue that that is also better for data privacy because you don't need to access the data set. You can just generate new data from it. But for this paper, yeah, we just find the top 10 nearest data points with respect to Z star. Now, we said that now the decision, the data might go through a distribution shift. So graphs might change their structure or completely their underlying class. So for example, a graph in the previous snapshot that contained cycles in the next snapshot might not contain cycles. And if we have a binary classification where we want to know if a graph has cycles or not, then something has completely changed. So we need to update the counterfactuals, which might have been invalidated in time. Now, again, we don't want to rely on the underlying oracle. We relied on the oracle only on the first snapshot to build these class representation experts. And now we want to rely, let's say, unsupervisedly on the class representation experts. Because what has happened in the first snapshot, we argue that these two class representation experts have actually learned the oracle decision boundary, okay? And now we want to just use them. Now, what we can do is we can use learned representations of the variational graph autoencoders. And for each graph that comes in input, we do this, we find the counterfactuals. So we get the K counterfactuals, which are close to the center. And what we can do is we can use these counterfactuals to update the knowledge of the variational graph autoencoder, which is responsible for learning the counterfactual data. And we can use the graph itself, because we know the class y hat, we can use the graph itself to update the variational graph autoencoder, which is responsible to learn the class itself. Okay? And this goes in also other snapshots. And by basically by using this at inference time, by using this search, let's say, property in the latent space, we can update these two variation graph autoencoders simultaneously in a semi-supervised fashion. Sorry, in completely unsupervised fashion in the next snapshots. And in this way, we can also emulate the fact that the decision boundary of phi of the oracle phi can undertake changes or distributional changes. Okay, so this basically helps us to factor that in, and we want to do it by not relying on the oracle phi. I'll just show you some of the experiments of what we had on for this paper. Obviously, the paper had to be state-of-the-art, otherwise we wouldn't be publishing KDD. We used one synthetic data set, which is this dynamic 3 cycles. So it's like a binary classification data set. All of them are binary classification data sets, but this one, just the underlying classification problem is state whether a graph has cycles or is a tree. Okay. So this is the first data set. DBLP is just a co-authorship data set, and the underlying problem, classification problem, is whether a clique of authors has more contributions, so has more collaborations with respect to the average of all collaborations in that particular snapshot. BTC, alpha and beta are just two versions of Bitcoin transactions, and they're actually in these scenarios, users do some transactions with one another, and they rate whether the transaction was actually good or fraudulent. And given a specific node, we can see whether its outgoing transactions have been voted as fraud, and that particular ego network of outgoing is going to be fraudulent, so it's going to be labeled with 1, and if it's not, then it's going to be labeled with 0. These are just two different versions of the same data set, and Bonanza here, B and Z, is just another data set which resembles eBay and user feedback on buying products or buying items. So if you get an average score of, I think, less than 4.2, then you're just a bad seller. And if you get, sorry, a score which is higher than 4.2, then you're a good seller. We outperform everything, so that's pretty neat. Some of the models here presented, some of the counterfactual explainers here presented are not let's say time-based. Just digress does this update mechanism as well. Whether the first models are time irrelevant, so they're just trained on the first snapshot of the data set, and then they're just used as is to find counterfactuals on the other snapshot. And you can see that some of them don't even converge after 14 days of execution in a great cluster. We also show that our performances are actually statistically and significantly different on all data sets on average, because we basically have these p-values. We do a Dunn test with a Dunn test with Bonferroni and without Bonferroni to see whether we are statistically better than the rest. You can also see first time snapshot performances on all of the data sets. We measure validity at 1, which means if the first candidate, the first counterfactual candidate is an actual counterfactual, so it satisfies the first necessary condition of being counterfactual. We also measure graph edit distance of the first candidate, meaning that we not only want to be correct, but we also want to be very similar in terms of graph edit distance with respect to the input graph. And we see that we actually have quite good performances in terms of validity, although in some of the data sets, validity is very difficult to obtain very high because they're very challenging. But we outperform the state of the art, and yeah, I mean in most of the time snapshot, not just on average. We do require a fair amount of graph edit distance, but that's because some of the graphs that come from, for example, from DBLP or Bonanza or these Bitcoin transaction networks are very heterogeneous, and we might not have seen the whole representation of each of the classes. That's why we might have not mapped them correctly towards the center, but maybe instead of staying nearby the center, they might have been just dispersed around the center. That's why we have a lot of graph edit distance here.
Just a question for the validity at 1.
Yeah.
Should we expect the performance to deteriorate as you see more snapshots, or they should actually go up as you see here?
So the most interesting cases are, for example, this one here, DBLP and BTC beta, because that's a cool observation. Because yes, if there's a complete data shift, then your validity should go down. What happens in some of the cases, the data shift is so subtle. So, for example, in this synthetic data set or DBLP, which is pretty easy, in BTC, which is pretty easy, the data shift is so subtle that you just don't care. And also, if you see the other methods here that have been trained only on the first snapshot, so for example, this is MEG, it still has an increasing performance because the shift is not that let's say disruptive as one might expect. The best case scenario is if you have a horizontal trend, and here you can see that there's actually not that kind of much of a difference. So 0.5, 0.55. So the endpoints, even though you might have like squiggly lines, at the end of the day, you just have like a flat trend besides this one here.
I see.
Yeah.
Thanks.
Okay. Again, we had this sampling factor of counterfactual candidates. And if we sample more than one counterfactual, and we measure the validity that at least one of these counterfactual candidates, sampled candidates from the latent space, is a valid counterfactual, then we have just increasing. So the more we sample, the more the validity at K grows, because at least one of them is valid in that set. And this is across the board, with some of the outliers going from these kind of transaction networks, so with the Bitcoin transaction networks. And you can actually see in more detail what are the outliers for each of the time steps on the number of counterfactuals. So you can have that in 2010, 2011, 2013, which were these snapshots, they were the performances that were the least robust for BTC alpha, and for the BTC beta, you have the 2011 snapshot, which was the least, let's say, performing in terms of validity at K. But the gist of these plots is the more you sample, the better the chances that you have a correct counterfactual. I want to just move quickly, and then I can conclude, to the effect of the pooling factor. We saw at inference time that when we map a graph to the latent space Z, then we use this pooling factor lambda to pull it towards Z star. And what we would expect is that the more we pull, the more valid we are. Okay, meaning that the more you go towards the center, the more are the chances of you going to get a valid counterfactual. And the pooling factor here is just reversed. So meaning that if you multiply the pooling factor lambda here by the latent representation Z by 0.3, you're actually pulling more. Okay. But what might happen is that there's this inherent trade-off between the validity and the graph edit distance, because what might happen is, because the counterfactual was so the original data sample was pulled towards the center of the latent space, the farther away the counterfactual is. So the more the graph edit distance, the more valid, but the more the graph edit distance. So we found this trade-off, whether you want to be very nearby or you want to be correct. Okay. We did some, and this is the last slide, I think, or the 2 slides more, and I'm concluding. I think that there's a bit of a difficulty on how to show the effect of counterfactual explanations with respect to the input graph if we have multiple nodes. Because then just by plotting a graph, you just have everything that is smushed together and you don't know what happens. So we would like to, at least this is one of the first papers that I've seen to do this, to propose a new method on how to show graphs. And what we do here is you see these squares, and each of these squares has denotes an adjacency matrix. No, denotes an adjacency matrix of the input graph and of the input graph. So it's an n by n. Each of the pixels here, for example, here, denotes an edge. So here we're showing only structural differences. And a black box represents that edge of the original input graph has been also in the counterfactual. A red cell denotes that the original edge was deleted, and the green cell, it means that we added a new edge in the counterfactual, right? So this is a quick way of represent, and whites means that there wasn't an edge to begin with between those two nodes. This is a quick way to see how what is the difference between the input graph and the counterfactual that you generated, and what are the operations that you're supporting. See that if you have an adjacency matrix, so, which is predominantly green, you see that there's more green. So it means that there's more addition edges happening. And if you see which is something that is more red, it means that you're just deleting edges. The cool thing about this is you can also see the graph edit distance, because what you want, what is the most optimal case, is that you just have at most 2 pixels, so the two different cells, which are either red or green, that helps you change class. So the more changing operations, so the more perturbation operations that you're doing, the more it will be seen on these kind of matrices. You can also see the correctness of each of the of your explainer, which means that basically every empty cell represents a failure for your counterfactual explainer to find a valid counterfactual. Okay, and these all counterfactual are just the first sample counterfactuals, so you can clearly see what happens in time and at each of the data samples. This is just an illustration. There's plenty of more of the samples, but this is to show you probably a failed scenario because you're having very low validity, but just to show you how you can represent changes in counterfactual. Lastly, we also saw that there's a state-of-the-art method which is optimized, is a heuristic base, but it's optimized to minimize the graph edit distance or the similarity between the input and the counterfactual if it finds it. And we wanted just to see what were the differences between the counterfactuals produced by us and by them. So each of these now matrices represents a counterfactual example with their adjacency matrix. A black pixel represents that the edge between Gracie and BDDS is the same. So these two counterfactual explainers agree on that edge. A blue pixel means that Gracie has added an edge, whereas BDDS didn't. And an orange one means that BDDS added an edge and we didn't. So Gracie didn't. A full orange block means that BDDS found a valid counterfactual, whereas Gracie didn't. And the blue one shows that we did, but Gracie didn't. A white cell means that nobody found anything. Now you can see that the agreement between the two is very low. So there's completely two different strategies of finding valid counterfactuals. And this is neat because you can also have two different counterfactual explainers just qualitatively be compared with one another. So I think here we are better than BDDS because we have more blue singular cells, meaning that also supporting our quantitative experiments where we have more validity at one. But you can see that we have more, let's say, graph edit distance with respect to BDDS, as also shown in the quantitative result. To conclude, Gracie is one of the first generative approaches to address dynamic counterfactual explainability. We leverage variational graph autoencoders self-supervisedly to learn class representations. We have an improvement of at least 13% in producing valid counterfactuals with respect to the second best performing state-of-the-art explainer. And in future work, I think that the center of a latent space of any kind of reconstruction-based methods should be used to find valid counterfactuals, because this was a preliminary study which showcased that there's potential in using the latent space into finding counterfactuals. thank you. If you have any questions, I can answer it now. I can take them from now.
Um, yeah, so thanks for the excellent talk. It was very interesting and very nice. Um, and for the audience, if you have any questions now, feel free to type in the chat. So the reading group is scheduled to be 1 hour. We are slightly over time now. So if you have any question, just answer like just ask them now for quick questions. So I have one final question, but it's not necessarily too related to the work, but it's so I understand that you pick GCN as because it's standard model for GNN.
Yeah,
But
yeah.
we know that GCN is limited in differentiating between different category of graphs. Like
Yeah.
it's limited in expressiveness. So do
Mhm.
you think that some of the performance, like some of the low performance data set could be bottlenecked by the expressiveness of the GNN rather than the setup of the framework?
Yeah. So we also tried. So just to answer your concern about this expressiveness, we also tried graph attention networks. We also tried stage as a component of or as the encoder, and we found out that because the graphs are very small, what happens is that they try to they just have a how's it called, a small receptive field, meaning that most of the node representation then just became completely averaged, and we didn't have any benefit. And we tried this empirically,
Right.
probably with larger graphs, like graphs that are more than, let's say, 10,000 nodes, the GCN would fail, and we would have to experiment there. Does that answer your question?
Yes. So it's more like just curious. And nice to know
Yeah,
that like you have tried the other variations.
yeah,
There is one question
yeah,
from the audience, and you might want to take that. Yeah.
yeah. So the question is, you mentioned edit distance. How do you deal with isomorphism? Still a beginner question. No, this is a great question. So if you measure edit distance here, um, here, sorry, here, if you measure edit distance, isomorphism, you're not going to take it. So if a graph is isomorphic to another one, your edit distance is going out of the roof. One quick thing here is that you can embed the two graphs into another latent space, maybe with a frozen encoder. I don't know, you can use maybe a graph attention network or Sage just to embed them in a common space, and then you just can measure their cosine similarities, I guess. And that takes care of isomorphism, but graph edit distance doesn't. So good point here.
Okay.
Cool.
Great. So thanks for the great presentation. Let's thank our speaker again, and then we'll wrap up and see you next week at the reading group.
Thank you again for having me.
Thank you. Thanks, everyone. Bye.